Hello everyone. It's a pretty good crowd for Thanksgiving week, so happy to see you. So today we'll build on the Z transforms that we started discussing last time, and we'll start analyzing linear time invariant systems in discrete time with Z transform methods. So the key feature of LTI systems is that for them the convolution property works, meaning that if you know the impulse response to your system, h of n, then whatever input may come in, the output is given by a convolution operation of the input and the impulse response, right? Now, what does this mean if we take Z transforms? The convolution property of Z transforms says what? That y of z, the Z transform of the output, is equal to, come on, I mean, seriously? H of z times x of z, right? So that's the famous convolution property of pretty much every transform we studied so far, right? Important property. So what is h of z? H of z is the Z transform of the impulse response, which by definition is equal to the sum from negative infinity to infinity of h of n z to the negative n. But we have seen this before when we talked about the response of LTI systems to exponential signals. We saw that any exponential signal like z to the n is like an eigenfunction for an LTI system. The output will be again z to the n multiplied by a coefficient. And what was that coefficient? It was h of z. We called it the transfer function back then. So now the transfer function reappears as the Z transform of the impulse response, just like the transfer function of a continuous time system appeared as the Laplace transform of the impulse response. All right, so these are two important things. So the output is, when you work with Z transforms, you just multiply things, the Z transform of the input with the Z transform of the impulse response. Okay, so that's just a quick reminder of these properties. So what I want to discuss really first is how do we determine stability from h of z. Or that wasn't really a question, it was a statement. All right, so how do I determine stability if I give you h of n, the impulse response? What's the test? So the absolute summability property, right? So that's the necessary and sufficient condition for stability based on the impulse response. We need to translate this to a property of h of z. So how do we do that? Well, there are two key observations. First is that this indicates, this is equivalent to the unit circle being inside the region of convergence of h of z. Does that make sense? Because when you are on the unit circle, you're multiplying it with e to the j omega n. Z to the n looks like e to the j omega n, whose magnitude is 1, right? So the convergence condition for the Z transform boils down to this absolute integrability condition. It was a very similar result for Laplace transforms. We want the ROC to contain the imaginary axis, right, for stability. for absolute integrability. So that's the key condition. So we want the unit circle to be inside the ROC. But what is the ROC? We are going to restrict our attention to causal systems. What does causal mean? How do I judge causality from H of n? H of n should be 0 when n is negative, right? So last time I mentioned that when we talked about some of the properties of the region of convergence, we mentioned that if it's a right-sided signal, then the ROC starts with the outermost pole, the pole that's farthest from the origin, and extends to infinity. Okay? So therefore, we can carry over that property to this signal h of n. So ROC of h of z extends from outermost pole to infinity. All right, so we have two observations. First, if you're talking about causal systems, which is our main interest in this course, then the ROC extends from the outermost pole to infinity for h of z. And stability means that the ROC should include the unit circle. All right, so the two properties pictorially mean the following. The first one means that, well, the second one basically means that, whatever the poles may be, the outermost pole determines the ROC. So the ROC is the exterior of that. All right? All right. So, and then we want the unit circle to be part of the ROC. Okay? So that means the unit circle should lie somewhere here. Unit circle. All right, so this is a picture where things work, right? Things come together. Unit circle is in the ROC, and ROC, since the system is causal, starts from the outermost pole and extends to infinity. All right? So then if you look at the picture and forget about the ROC, just erase from your memory the ROC, what are we left with? Where are the poles relative to the unit circle? They're inside. Okay, so ROC played an intermediate role to help us derive a condition. So the stability condition, therefore, is that all poles must be strictly inside the unit circle. What do I mean by strictly? I mean that you can't be on the unit circle, because then this dashed circle in the interior coincides with the circle, and the dashed circle itself does not include the ROC. Remember, the poles cannot be in the ROC. So that means the unit circle would not be part of the ROC, so our test would fail. Okay? So is that a meaningful condition that you can't have poles on the unit circle? Yes, indeed, that leads to instability. So here's a simple example. So just to emphasize, no pole on unit circle allowed for stability. So here's a simple example. Let's say h of z is 1 over 1 minus z inverse. How do I find the pole of this? I can write it as z over z minus 1. So there's a pole at z equals 1. That is on the unit circle, right? So according to our stability condition here, that is unstable. And what does unstable mean? There exists some input, some bounded input, that will drive the output to infinity. And what might that input be in this case? There may be more than one, but just give me one. No, but we want a bounded input to convince ourselves this is not stable. We want a bounded input that gives us a bounded output, unbounded output. Constant, yeah, unit step. So if you think about it, this is the z transform of what? This h of z. Huh? If there was a little a in front of z inverse, that would have been a to the n times u of n, right? If I fix a to be 1, that's just u of n. So this is the z transform of the unit step. Okay? So if I choose as my input, so this is by the inverse z transform basically. If I choose my input another unit step, then the output is unit step convolution with unit step. That doesn't sound good in terms of boundedness, right? Because what you're doing is you have one unit step, you're flipping the other, dragging, right? So, I mean, this is a continuous looking picture, but the same thing. So, as you keep dragging, there's no limit to the area, right? It will grow into infinity, okay? So that will be unbounded. All right, so that's the idea. In fact, you know, you can do, if you really want to explicitly find the convolution without finding y of, without doing a convolution, you can just multiply 1 over 1 minus z inverse with itself, because that's x of z. So the squared term is the z transform of the output, and now you can do an inverse z. And it's going to give you something like n times u of n, a linearly growing term. Okay? So we did these, followed from the derivative properties in the last lecture. If you have something squared, a term like this squared, the inverse z transform involved a multiplication with n. That's why it grows unbounded. Okay? All right, so there is a good reason, therefore, to exclude poles on the unit circle, just like we excluded poles on the imaginary axis. So it's good to go back and compare the pictures. So these are the stability regions for continuous and discrete time systems. For continuous time systems, we are in the S plane. And for discrete time systems, we're in the Z plane. For the S plane, the left half plane is where the poles should be for stability, and they should not be on the imaginary axis. In the Z plane, you should be inside the unit circle, and you should not be on the unit circle. All right, any questions? Should be straightforward, right? Okay. So let's go back now and talk a little about an important class of LTI systems. Those are systems described by difference equations. So what we want to do is when we see difference equations, we want to be able to look at it and immediately write a transfer function associated with it. How do we do that? Well, it's very similar to what we did for differential equations in continuous time. So a difference equation model for an LTI system would have this form. Coefficients AK multiplying the output, the delayed versions of the output, right? And then the right-hand side depends on the input and its past values. So K goes from 0 to M. All right? So how do I turn this into a transfer function? Well, transfer functions are intimately connected to Z transforms. So if we take the Z transforms of both sides, we should get to the answer. So there's the superposition principle of Z transforms like any other transform. Therefore, if I take the Z transforms of both sides, I'm going to get sum over 0 to n AK times the Z transform of Y delayed, right, by K. And the right-hand side will be the weighted sum, again using the linearity property, of z transforms of x of n minus k. Right? So what is that? What is the z transform of yn minus k? Take k1 to begin with. So we're talking about y of n minus 1. Y shifted by 1. What happens to the z transform? It's multiplied by z inverse. Remember, delay by 1 unit is z inverse. Okay? We have no reason not to remember that. So that is going to be k delays, therefore z to the negative k times y of z. Okay? And this likewise is z to the negative k times x of z. All right? So I can factor out y of z. In the left-hand side. And then do the same on the right-hand side. So x of z factored out, right? And I know that y of z by x of z from this expression here, oops, why am I crossing it? From this expression here, y by x is going to be h of z. So therefore, y of z by x of z is our transfer function, h of z, which is going to be the ratio of these two polynomials in z inverse. So let's see. So the b terms will remain in the numerator. So I'm going to now write this out explicitly in the numerator. So this reads as b0 plus b1 z inverse to bm z to the negative m, right? And in the denominator, I'm going to get this term, which I can write explicitly as a0 plus a1 z inverse to an z to the negative n. Okay? So that's the transfer function. Now, we cannot forget about all the intermediate steps and just remember the connection. Here is the difference equation. Here is the resulting transfer function. All right? Now, you can observe that the coefficients that multiplied x, the input, went in the numerator, became coefficients of a polynomial in z inverse, and the coefficients that multiplied y in the difference equation went in the denominator. So it's good to remember that pattern, although this is fairly easy to derive. You shouldn't have to do that every time you have to solve a problem of this nature. So as a simple example, if I tell you my difference equation is y of n minus 1/2 y of n minus 1 equal to x of n plus 1/3 x of n minus 1. What is the transfer function? Of course, I'm not going to do everything I did about to derive a general expression, so I'll just apply the general observation from that formula to this example. So, the coefficient of yn, which is 1, goes here. That's the a0 in the formula. Okay? The coefficient of yn minus 1 multiplies z inverse in the denominator. So all the y terms get carried to the denominator. The coefficient of x is 1, so we get a 1 in the numerator. And then the coefficient for xn minus 1 is 1/3, so we get plus 1/3 z inverse. So where is the pole and where is the 0? No, I meant 0 and pole. So where is the 0 of this system? And 1/2. So generally we're going to see terms like this. 1 plus some coefficient a z inverse, right? All of these are of this form, right? A is 1/3 in the numerator, a is negative 1/2. That implies that z is equal to negative a, right? Because if you substitute z equal to negative a, then you have a times a inverse with a negative sign, and that's negative 1, cancels the 1, you get 0, right? So it's good to remember that structure as well. So whatever coefficient we are seeing here, that is a pole, except that the sign has to be reversed. This is a pole, except that this negative 1/2 has to be positive 1/2. Okay, so that's fairly easy as well. So now we'll talk about how we can evaluate the frequency response from a transfer function. So remember again that if I give you a transfer function h of z, all you have to do to recover the frequency response is substitute z equals e to the j omega, right? That's why we said when we were talking about discrete time Fourier transforms, we wrote it as h of e to the j omega, so we could easily link it to z transforms later on. Now the moment has arrived, okay? So now you understand that notation, right? So that way I don't have to have a separate notation for the frequency response and a separate one for the z transform. They are both h, right? When I substitute z equals e to the j omega in the z transform, I just recover the Fourier transform. All right, so okay, so we're going to look at what to expect. You know, how do the poles and zeros of the transfer function affect what the frequency response is going to look like, right? So let's say I give you a transfer function h of z that looks like this. That's the general form we just discussed, right? Associated to difference equations, be mz to negative m. All right, and then you'll have similar terms in the denominator. How many zeros does the system have? Capital M, and it's going to have capital N poles, right? So what we can do then is, remember, we can decompose each term into something like this. So zk, z inverse. So product of these things from k equal to 1 to m. So that means I can factor it out into m terms like this, where I would directly read out the zeros from these coefficients. So this is the kth zero of the transfer function, right? And then I can factor out the denominator in the same manner. So I'll get the product from 1 to n. I'm going to give it a different name, coefficient d instead of c, z inverse. So therefore, this coefficient here becomes the kth pole of the system. So by factoring out what I have in the numerator and the denominator, I can explicitly display the poles and zeros. But of course, if I factor out in this form, the leading term will always be 1, right? Because I'm multiplying things like 1 minus c z inverse. Multiply as many as you want, the leading term is still 1, right? Not b0. So to be able to bring it to this form, first we would have to factor out b0 from the numerator and a0 from the denominator and factor out what remains, okay? So that's the first step. So b0 and a0 have to come out as a coefficient. All right? So why is this form useful? It's useful because if I ask you what the frequency response is, then you can say, well, this expression here is really a product of a number of things, right? Each of which is a complex number or real. So therefore, if I'm interested in the magnitude of h, I just multiply the magnitudes of each term that is getting multiplied or being divided, right? So b0 by a0, we look at the absolute value of that. And then we look at the absolute value or the magnitude of each of these terms here, which is 1 minus ck e to the negative j omega. Okay? And then the denominator gives us k1 to n 1 minus dk e to the negative j omega. All right, so that's just an observation. As it is, it's not that useful because what do each of these terms look like? We still don't know that. But actually, that's not hard to interpret. So what is a term like if I pick, just one of the poles, right? So what does, let's say one of the poles, 1 over 1 minus dk e to the negative j omega look like as a function of omega? Any ideas? Let me give you a little hint. Let me write this as, let me try to factor out e to the negative j omega from this, right? Times e to the j omega minus dk. And if I multiply two complex numbers and take the magnitude, look at the magnitude, it's the product of the magnitudes. And what's the magnitude of this guy? It's 1. So that goes away, right? So we're interested in 1 over e to the j omega minus dk. What is that geometrically? Where does e to the j omega fall in the z plane? It falls on the unit circle, so let's make a circle here. So, and then the real and imaginary axes. Not the best plot, but it's okay. And so e to the j omega is a point here. That makes an angle of omega with the real axis, right? And dk is a pole. So let's say it's a real pole between 0 and 1, so it's stable, right? It's inside the unit circle, so it's stable. So how do you interpret e to the j omega minus dk? That is a vector, right? In the complex plane that starts at dk and ends at e to the j omega, right? E to the j omega minus dk is the end point minus the beginning point. Therefore, it can be interpreted as a vector, right? Let's call that vector v1, okay? So therefore, this is equal to 1 over the length of that vector. Does that make sense? All right, so then just by that intuition, you can make a rough plot of the magnitude of the frequency response. So let's do it together. So what is h of e to the j omega? So e to the j omega, when omega is equal to 0, is a point here, right? At that point, v1 is the distance to dk. It's this distance here, right? And now let's say we start moving omega from 0 to pi. So we're moving in this direction. And let's say pi is this point. Okay, so how is that going to change? What happens to v1? So you're taking a stroll on this circle, right? And you're measuring your distance from that pole, which doesn't change, right? So as you walk, what's happening to your distance to the pole? Start small, because you start at 1, and it ends sort of bigger. It gradually increases, right? Therefore, 1 over that distance is going to start big, and it will decrease as we reach pi. Okay? So it's going to look like this. Yes, so it would look like something like this. Okay? So that's what happens if you have only one pole. But we can generalize this picture to systems that have multiple poles and zeros and see what kind of frequency responses we can expect. We were doing something very similar in continuous time systems. We were walking on the imaginary axis, right? Because we were looking at j omega, and we were looking at our distances to the poles and zeros, and multiplying the distances to the zeros, dividing by the product of the distances to the poles. And that we interpret as the magnitude of the frequency response. So let's take a specific example with a particular choice of poles and zeros. So let's say h of z is 0.05, 1 plus z inverse by 1 minus 0.9 z inverse. Before I do anything else, tell me why I have a coefficient of 0.05. Why must have I put it there? It's normalizing something. Something like that, yes. So the DC gain for a... So DC gain, let's remember DC gain. If I take h of j omega and substitute omega equal to 0 in continuous time, that's what it is, right? DC gain, right? So therefore, you know, it's the same thing as taking the transfer function, substituting s equals 0, right? So this is continuous time. In discrete time, DC gain means what we get when the frequency is 0 again. But in terms of h of z, that means setting z equal to 1, because e to the j0, e to the 0 is 1, right? So to find the DC gain for a discrete time system, you just plug in z equal to 1. So if I put h of 1 to see what the DC gain is, I'm going to get 0.05, 2 by 0.1, which is, did I do this right? Yeah, 0.1 by 0.1, 1, right? So this was really here to normalize DC gain to 1. Okay, so we get a nice frequency response plot with that starts at 1. All right. So now let me try to make a circle. You know, I'm really talented with that, right? Okay, so and then a straight line, another straight line. And let's mark now the poles and zeros here. Where do I have a 0? At -1. And I have a pole at 0.9, right? Okay? So then we do our experiment, the walking experiment. We start at 0, we walk around the perimeter, the circle, and then we measure our distances to the pole, and let's call that vector v1 as we did before, and let's call the vector that connects us to the 0 v2. Okay? So then h of e to the j omega is 0.05, which is just that coefficient, times the distance to the 0, which is v2, the magnitude of the vector v2, and the distance to the pole, which is the magnitude of the vector v1. So what do you expect to see? So when you start at omega equal to 0, I think there's a way to highlight this. So we start here. Okay, and then, I don't even know. Am I doing this? Yeah, okay. You could train a monkey to do this, but I'm having difficulty. Okay, so So take omega 0, you're here, and then increase omega to pi. So what is going to happen to the ratio of V2 to V1? Or individually, what's happening to V2 and what's happening to V1? V1 is growing, right? V2 is shrinking, and in fact, it hits 0 at pi. So when I hit pi, when I'm at this point, the distance to the 0 is 0, so the numerator actually vanishes, right? So therefore, our frequency response is going to have this form. And remember, in discrete time, we usually draw a frequency response from 0 to pi, because everything from that point on is a repetition. There is mirror image symmetry between 0 pi and pi to 2 pi, and 0 to 2 pi to 2 to 4 pi, they are just copies. So it's enough, therefore, it's enough information to plot from 0 to pi. And remember, pi is the highest frequency in discrete time. Okay, so where did I start? What is the DC gain? It's 1. And where did I end at pi? At 0. So, and then I'll gradually decrease and hit 0 in the end. So this is what h of e to the j omega will look like. This is a rough plot, but that's why we need this discussion anyway. We just want to get a general sense of how pole zero locations influence the frequency response. Do you have any questions up to this point? And of course, if I want to continue from pi to 2 pi, it'll follow by symmetry. All right, do you have any questions? So this example actually is, a representative example of a very simple first order low pass filter you can build in discrete time, right? Because obviously the low frequency is passed through, DC gain is 1, that's why we added that coefficient 0.05. So low frequency is passed through with unit amplitude multiplication, and high frequencies get smaller in amplitude. In fact, if you hit pi, you're going to be eliminated. So if this signal were to receive an input that looks like 1, negative 1, 1, negative 1, what do you expect at the output? 0, because 1, negative 1, that signal has frequency pi, right? E to the j pi n is negative 1 to the n, so it's a flipping signal. All right, so this is a low-pass filter. So this is an example of a low-pass filter. And in fact, here, I just want to give you concrete coefficients, but we could make this a lot more general if we left the pole as a parameter that we can decide. There is good reason to leave the 0 where it is. What is the reason? Yeah, because we want our response to be 0 at pi, right? So, and pi is like e to the j, so negative 1 is e to the j pi. So we left the 0 there exactly on the unit circle. There is no harm in putting zeros on the unit circle. Can I put poles on the unit circle? No, that's the problem. That causes instability. But zeros don't affect stability at all. They are irrelevant to stability. So it's okay to have a 0, and when we're designing simple filters, we can use that fact. If there's a frequency that we really want to kill, like pi in this case, we can put a 0 exactly on the unit circle at e to the j that frequency, in this case, e to the j pi. Right? So therefore, if I'm designing a general low-pass filter, I don't need to mess with that 0. I think it's fine where it is. But the pole is flexible. I chose it to be 0.9 for no reason, right? Other than giving you a concrete example. So now let's make this example a little more general by switching colors. So let's call that dk. It no longer has to be 0.9. Okay, so then how would I modify my transfer function? It would be, does anything change in the numerator? No, we still have a 0 at -1, so the numerator should stay as it is, 1 plus z inverse. Now the denominator is a little more general. Oh, I'm not going to, why am I calling it dk? It was dk when we had many poles. Let's just call it, let me see what I used in the notes. Yeah, let's just call it alpha. Okay, it's your choice. Okay, so if I have a pole at alpha, the denominator must look like 1 minus alpha z inverse. Now that coefficient that used to be 0.05, how should I modify it? The goal again is to make sure that when z is equal to 1, h gives you 1. So 1 minus alpha divided by 2, because if you set g equal to 1, the numerator is 2, cancels with the 2 here, the denominator is 1 minus alpha, it cancels, so we get 1. So that way h of 1 is equal to 1. Okay? So the rest of the story is really the same. So, you get a response like this. But I just want to ask you, how do you think, no matter what I choose for alpha, it is going to look like a low-pass filter, right? But if I move alpha around, qualitatively, what do you think will change in the frequency response? Let me make it a little more concrete. Suppose I drag this alpha, this pole, all the way here, pretty close to the 0. What do you expect to see then? Again, you have these two distances rather, and you're dividing the distances to get your frequency response as you walk from here to there, right? So what do you expect to see? It will be pretty close to 1. If the pole and 0 are close by, I can't put the pole on the unit circle. It has to be inside for stability, but I can bring it pretty close. I can choose it to be negative 0.9, for example, right? So that means when I'm here, comparing my distances, it's going to be pretty close to 1. In fact, it will be 1 because of the normalization factor. And, for small frequencies, still those two look pretty close to each other, right? Just like landing a plane, right? Two houses may look like the same distance to you, but when you're there, they are far apart. So, therefore, if I bring the pole here, I should have used a different color here. What's your favorite? It is green. You can do green. Okay. If I bring the pole here, then what changes here is that this is going to remain close to 1 for a longer range of frequencies, right? But as you get closer to where the poles and zeros are, now you start distinguishing your distance to the pole and 0. And as you hit here, you go to 0 because your distance to the 0 has become exactly 0. So the effect is that, you're just going to stay close to 1 a little longer. Okay? So what has changed? What feature of the low-pass filter has changed? The bandwidth, the cutoff frequency, right? Cutoff frequency is now bigger. So what happened here is that this alpha, the pole location, is now a knob, right, that changes the cutoff frequency. In fact, there's an expression based on this general, first-order transfer function. There's an expression for the cutoff frequency, or an expression that tells us how to select alpha relative to a desired cutoff frequency. And the formula is, I'm not going to derive this, but you can. It's not such a big deal. 1 minus sine omega c by cosine omega c. Omega c being the cutoff frequency, negative 3 dB, or 1 over square root of 2 cutoff frequency. So what that is the point, the frequency where you go from 1 to 1 over square root of 2. Somehow you declare that once you hit 1 over square root of 2, that's low enough below 1 that you consider that to be your bandwidth, right? So that is the cutoff frequency for the green plot. And for the blue plot, the cutoff frequency is here, right? So clearly you've increased your cutoff frequency. So if I look at this expression a little more closely, do I indeed observe that? Suppose I want to take my omega c, the cutoff frequency, close to pi, right? What's happening to alpha in this formula? Cosine omega c is going to -1 because omega c is going to pi, right? Sine is going to 0 because you're going to pi. So you're going to 1 by -1. You're approaching -1, right? So this is telling you that if you want to increase your bandwidth, bring it close to pi, then move your pole close to -1. If you want a smaller bandwidth, if you want a very small bandwidth close to 0, then omega c, then alpha should be close to 1, because sine omega c is then close to 1, right? Does that make sense? Yes? Okay, so, all right, let's take a few minutes of break for you to take this in, and then we'll look at some other simple filters like high pass, band pass, and all that. All right, I'll wait for you so you're on time. It would come from this. So you would have to do a little bit of, I guess, algebra. You would have to write h of e to the j omega, find the magnitude, set it to 1 over square root of 2, yes. Or it's easier probably to just plug this in and put z equals e to the j omega and convince yourself you're getting 1 over square root. Oh, that's easier. And if it doesn't check, tell me, because I haven't derived this in a long time. I was waiting for you. Okay. All right. Okay, we should start. Absolutely. All right. So this showed you the magnitude plot. Phase can be obtained similarly, although I don't want to draw new figures. So I'm just going to show you what I have here somewhere. Yes, here. So same problem really. Somehow alpha became A. That's fine. So we are now interested in the phase. Geometrically, the meaning of the phase here is the difference of the two phases. One is the angle you make with the real axis that the vector v1 makes with the real axis, and the other is phi 2, the angle of the other vector. So the difference between the two, phi 2 minus phi 1, is the phase of the whole thing. And clearly, if you look at what happens to phi 1, it starts from 0, goes to 180. Phi 2 also starts from 0, but it goes to 90, right? Because as you're approaching negative 1, you're going vertically. So therefore, the difference between them is going from 0 to negative 90 degrees. Okay? So we kind of de-emphasize the phase, for these examples and focus on the magnitude, which is here. But it's good to know how you would derive that if you had to. So with that, let's go back to an example that's not low pass. Let's do a high pass this time. But again, let's keep it very simple, based on our intuition. The only intuition we're using here is this geometric interpretation of the frequency response. Distance to zeros divided by distance to poles, right? So now my goal is to get rid of low frequencies and pass high frequencies. So if you want to fully eliminate the lowest frequency, omega equal to 0, DC, where would you put your 0? I heard the answer, but I want it louder. 1. Because at that point, omega is equal to 1. Your distance to the 0 will be 0, so the frequency response will start at 1. Okay, so we decided on the location of the 0, and then the pole, the only constraint for the pole is we're going to try to keep it real, and also it has to be inside the unit circle for stability. So let's say we, select the generic pole at, let's say, alpha again. So that can also be negative. Alpha can move from negative 1 to positive 1 without losing stability. All right? So, and then we claim that this is going to be a high pass. So let's first look at the transfer function. If I have a 0 at 1, what should the numerator look like? And remember, we try to write it as 1 plus something or 1 minus something. 1 minus z inverse. That way z equal to 1 makes it equal to 0, right? And then the denominator is going to show us the pole, and that hasn't changed. 1 minus alpha z inverse, that means you have a pole at alpha. All right? So when we put it in this form, what I want to do now is, of course, I'm going to need a coefficient here. How should I select it? The frequency response I'm expecting now is going to start at 0. Why? Because we have a 0 at 0, right? And then it will increase. And I know it's scary. I would do the same. Okay, so we want to pass high frequencies, right? So a unit gain there is appropriate. So to make that happen, how should I select the coefficient? H at pi. Pi means z equals e to the j pi, which is negative 1, right? So h of negative 1 must be equal to 1. This is not the DC gain now. This is the highest gain, which is h of negative 1, right? So Okay, so just to make sure everybody follow this, this is e to the j pi. Okay, so h of -1 is going to be, if I substitute -1 for z, that is going, the numerator will be 2, and this will be 1 plus alpha in the denominator. So the coefficient should be 1 plus alpha by 2. Do you all agree? All right, so if you don't believe me, substitute z equal to -1, and you'll see that h becomes 1. Okay? So in this case, we are looking at our distance to the 0, looking at our distance to the pole, and plotting the ratio of the two. Clearly, as we go to pi, this is going to level at closer. It will level, and then we've adjusted the coefficient so that it will level at 1. Okay? So phase can be derived similarly. So what is the cutoff frequency in this case? Turns out, strangely, the same formula works. So the formula that told us that alpha should be selected as 1 minus sine omega c by cosine omega c still works. It still makes omega c give us a frequency response of 1 over square root of 2. But of course, in this case, something is different. If omega c is coming close to pi, that actually means a small bandwidth, right? Bandwidth means the width of the band where we are passing the thing, right? In this case, that's what's happening between omega c and pi, right? So if I want omega c close to pi, that is a low bandwidth for the high-pass filter, I would have to, again, choose alpha close to, actually, I don't know the answer. So if I want omega c to go to pi, right? So same deal, right? Alpha needs to go to -1, correct? Is that right? Isn't that the same though? What has changed? So here, if I wanted omega c to go to pi, if I wanted omega c to go to pi, then I would have to choose alpha to be close to -1. It's the same formula. Nothing has changed, right? Yeah, I think it's still the same. No? That's right, yeah. Because then you're actually right. If alpha is close to 1, you're looking at this situation. These two guys are very close together. So near omega equal to 0, you're going to have a sharp change. But then already, once you start going away from omega 0, you'll level. So that's the case for a small omega c, right? And if you choose your pole to be on the other end, then you will remain closer to 0 for the most time and then suddenly jump to pi. Right? So I think, yeah, everything checks. All right, so that's our high pass. How do I build a band stop filter? Band stop means you no longer are trying to stop high or low. There's a certain range between high and low that you'd like to stop. These are also called sometimes notch filters. Now, I can tell you right away that, this one pole, 1, 0 business is no longer going to work. Okay? That's just too simple to give you this type of behavior. Notch means you want to go straight close to 1. You want to dive in to stop a certain range of frequencies. And you want to go out again and level around 1. Okay? You can't do that with 1 pole, 1, 0. It's just, you can't. Okay? So the lowest order filter you can accomplish this with is a second order filter. You'll need 2 poles, right? I think in the previous examples we already developed some intuition about what pole and 0 are doing to the frequency response, right? To stop a certain frequency, I can just put a 0 at that frequency on the unit circle and it will do the job. It will bring the frequency response to 0, right? What is the effect of the pole? If I put the pole close to the unit circle, what happens? as you're traversing, let's go back to this example. Actually, let's not go back to this example. So let's say that, let me draw a circle. Okay, so let's say that I have a pole here, okay? So what will happen when I'm near that frequency? So as we're going from omega 0, wrong thing, okay. As we are going from omega 0, and we're passing from the vicinity of that frequency, right? Your distance to the pole is going to be pretty small. But that makes the response large because it's 1 over the distance for a pole that matters, right? So that means as you come close to the pole, you're going to grow. Okay, so poles serve to emphasize frequencies, increase. But there's a constraint. I can't put that pole on the unit circle. I have to put it inside for stability purposes. Okay? Whereas zeros, you can put them on the circle. So you put a put a 0 on the circle at the frequency you want to kill, and you want to put a pole inside the circle, but if you want close to the circle, to emphasize the frequency. All right? So with that in mind, let's start building our notch filter. So let's say there is a frequency, omega naught, that I would like to stop. So I'm going to ask for your help to design the poles and zeros of a simple but reasonably good notch filter. So let's say I want the frequency response to look like this. As I go from 0 to pi, I want it to stop frequencies around a certain frequency. Somehow I have a grudge against that frequency, okay? So I don't want that to pass through. So I want a frequency response that looks like this, okay? That's the description of a notch filter, because you kind of have a notch around omega 0, right? So omega 0 is an angle here. And negative omega 0 is symmetric to that. All right? So that's the frequency I would like to stop. Let's start with our zeros. Where would you put your zeros? Remember, it's kosher to put zeros on the unit circle. You mean on the unit circle at those frequencies. So you're saying put one here? Okay. And then another one here. So it's a complex conjugate pair. So the product of the two terms, giving us these poles, will give us real coefficient polynomial of second degree, right? So this point is e to the j omega naught, and this point is e to the negative j omega naught, complex conjugates. Okay? So then h of z is, I'll have to go to the next page, but we can come back. So when we design the numerator of h of z, it's going to have 1 minus e to the j omega naught z inverse, because that's how we represent poles zeros, right? So this coefficient here, it becomes the 0. And then 1 minus e to the negative j omega naught z inverse. So that's what goes in the numerator. So the nice thing about poles and zeros coming in complex conjugate pairs is that when you multiply out terms like this, all those complex terms disappear. Everything becomes real. So we'll come to the denominator. We'll talk about the coefficient, but let's multiply out what we have in the numerator. So what do you see? There's going to be a 1, right? And there'll be, what are the z inverse terms? What goes into z inverse? Is that it? Okay. And then what is the z to the negative 2 term? It's the product of e to the j omega naught and e to the negative j omega naught, so it's just 1. Okay? So, and then what is this equal to? This term here? 2 cosine omega. As you can see, all the coefficients are real, right? That's why when we have real coefficient polynomials, the roots come in complex conjugate pairs. Okay, so we designed our numerator. I can start with the omega naught I want to kill, make that coefficient 2 cosine omega naught, and the numerator will be that. All right? And let's design the denominator. So I'm not going to, make that too prescriptive where to put them. But if you want a very sharp notch filter, sharp meaning that a small band width where you, or a small band stop width, meaning that you want this notch to be really sharp, right? How would you select your poles and where would you put the poles if that was your goal? You want to dive quickly and rise back quickly. You want to forget that happened, right? So you want a small, very small range where this dip occurs. Yeah, pick it pretty close to the pole, right? I mean 0. But inside, of course, that's our stability constraint, right? So put it somewhere here. I'm not going to, this doesn't have to be exactly there or there, but if you put it close, then as we are doing our walking experiment, measuring distances, here we'll be very sensitive. We'll dive down and then come back up. But once we're past this region where the pole and 0 are together, we'll be pretty oblivious to what happened there. We'll forget about that. Again, the distances to both will look almost the same. Therefore, we'll go back to 1. Okay? So putting the pole close to the 0 will make it a sharper. Sharp not in the sense of, quick transition, but it means a smaller width of the stop band. Right? So to do that, there's one parameterization of the denominator. So first of all, we call this number beta in these notes anyway. This is defined as 2 beta. So cosine omega naught is defined to be beta. It just becomes a coefficient. And then the denominator has this form. I'm not going to say too much about the denominator, except that we'll interpret what this beta is doing. I'm sorry, beta I already know what it's doing. It comes from cosine omega naught times 2. What is alpha doing? 2, yes. If alpha was equal to 1, what would happen? If alpha is 1, the numerator and denominator are the same things. So that means you put your poles exactly where the zeros are. That's actually not allowed, right? I can't put them on the unit circle. So, in fact, alpha has to be limited by 1. And in this design, beta is also limited by 1 because we are selecting, beta means cosine omega naught. That can't exceed 1. Okay, so the general form of the filter is this: 1 minus 2 beta z inverse plus z to the negative 2, and then this denominator. And alpha and 1 both have to have magnitude less than 1. The thing to know about beta is that if beta comes close to 1, that means you're bringing your poles closer to those zeros. Therefore, you're going to have a smaller bandwidth where around omega naught that you actually stop. If you put the poles farther away, then that will stretch. Okay, so there is, in fact, I think a formula somewhere. Well, no, I don't give a specific formula. All right, that's fine by me. No formula for how to select alpha. Okay, so the only thing I want you to observe is that as alpha goes to 1, the width is going to get smaller, and I already made that point. Now, the only thing we have not selected yet is the coefficient here, or the coefficient here. So what would we want in selecting that? I want this to be 1, and I want that to be 1 too. Right? So that means I'm going to want h of 1, that means 0 frequency, to be 1. And that means I also want h of negative 1, that means the highest frequency, pi. I also want that to be equal to 1. This particular parameterization of h is in a form that you can make h equal to 1 both at z equal to 1 and z equal to negative 1. Right? That's one of the reasons why the denominator appears in this funny form with 1 plus alpha alpha and all that. So it's adjusted so that you can, with your choice of alpha, you can actually set both of the coefficient, you can set both equal to 1. Okay? All right, I'm not sure if that was clear. So the reason that the denominator is written in this form, with this 1 plus alpha, alpha here, etc., is so that when you look at the frequency response of the thing, you go back to where you were at 0 frequency at the high frequency. Okay, so there's no discrepancy between those, right? Okay, so we still haven't answered the question, but we have two constraints. H of 1 must be equal to 1, and h of negative 1 must also be equal to 1. So, and to remind you, what's in the denominator is 2 beta z inverse plus z to negative 2, and 1 minus beta, 1 plus alpha, z inverse, plus alpha z to negative 2. So if I put z equal to 1, what happens? This will be 2, 1 minus beta in the numerator, right? And what else? 1 minus beta, 1 plus alpha, plus alpha. Is that correct? Yes? Okay. So you can see that there's a 1 plus alpha factor in disguise in the denominator. So it's really 1 plus alpha times 1 minus beta. Because here's a 1 plus alpha here, and this guy is a 1 plus alpha factor, so you can write it in this form. So then you have 2, 1 minus beta. Those guys cancel. That means I want 2 by 1 plus alpha to be... No, I don't want it to be anything. I just want to put 1 plus alpha by 2 here, so that that cancels and h of 1 is indeed equal to 1. Okay, so that will do the job. Okay? Now, let's look at h of negative 1. Then what do I have when h is negative 1? This time I have 2 times 1 plus beta, is that right? And in the denominator I have 1 plus beta, 1 plus alpha, plus alpha. I hope I'm doing this right. So I think it looks like this again. 1 plus alpha, 1 plus beta, 2 times 1 plus beta. Okay, again things cancel. Again, this gets set to 1. So that's what I was saying about the specific form of the denominator. So we already committed to a coefficient here, right? By trying to make this happen. So it was kind of lucky that that same coefficient made this happen as well, but it's not sheer luck. It's actually because of the particular parameterization of the denominator that we can achieve that. And that's why the simplest form of the notch filter has that particular form. All right, so now let's talk about a band pass. Now I want to pass omega 0 and kill everything else. So this is the desired frequency response. Omega you jump, go back to pi. And you want to jump when omega is the frequency that you want to pass. And you want the value there to be equal to 1. So this is the desired h e to the j omega. All right? I'm going to give you a circle and ask you to think about it. How would you design that? Where would you put your poles and zeros? Okay. Take a minute to think about it. Start with the zeros. If it's clear where you want to put your zeros, you can also think about where to put your poles. But first and foremost, I want you to think about the zeros. Okay, tell me about the zeros. Where do you want them? There's a clear hint here. You want this to be 0. You want this to be 0 as well. This is omega is 0, which means omega is equal to 0, which means z is equal to 1, right? And this means omega equals pi, therefore z is equal to -1. How do I make the response exactly 0 at those points? I put zeros at 1 and -1. Okay? That will ensure you start here and end here. What happens in between will be determined by the poles. But now, knowing where the zeros are, I can already write the numerator. So h of z is going to be some coefficient times 1 minus z inverse for the 0 at 1 and 1 plus z inverse for the 0 at -1. Okay? So, all right. So the denominator will have the same form that we discussed in the previous example. Where alpha is cosine omega 0. And omega 0, remember, is the frequency we want to pass. Right? So the only thing that's left to do is to determine the coefficient. to this coefficient here, right? So to do that, the constraint is we have to set, when z is equal to e to the j omega naught, we want to get 1 in the magnitude, right? So that's the idea. I'm thinking how we actually do that. I know the answer, I'm just blanking out on how to argue that. The answer is still same thing, 1 minus alpha by 2. And why is it that, so the poles are here, not exactly on omega naught, but somewhere near. But somehow that arrangement gives us the peak at omega naught with value equal to 1 if I select the coefficient in this way. All right, so I guess we could do this. Just substitute z equals e to the j omega naught and look at the magnitude. Should I try, or am I going to mess this up? I have a feeling I'm going to mess it up big time, but can we simplify first the numerator of this? What does the numerator look like when it's simplified? When you multiply out these two terms in the numerator. Z to negative 2, right? And the denominator is the same. Z inverse plus alpha z to negative 2. Yeah, I think there has to be a clever argument somewhere to show that we reach the value 1 when we substitute this. Okay, so if you substitute it here, you should get equal to 1. Does anybody see why that would be true? All right, that might be a good homework problem. I have to think about it somehow. Yeah, that's what I was thinking, yes. But then there's this alpha term there. Oh. Oh, yeah? Okay. Okay, I'll make the hint in the homework problem. Okay, it works. We'll see why. I'm making a note to myself. Homework. No, there's some cancellation, something like what happened in the band stop. But anyway, I will actually work it out on my own and give you enough of a hint to proceed. Okay, so with 2 poles, 2 zeros, we can now design band pass or band stop filters too. That's pretty good, and that's the smallest order you need anyway to design that kind of filter. Of course, you can get much better filters, much higher quality filters. I mean, the ideal band pass would look like this, right? So you have a region, a certain bandwidth prescribed, and you pass that and nothing else, right? Obviously, what we are doing here is building a very rough and cheap version of that, all right? But still, you can call it a band pass. Okay, so moving from very simplistic filters to somewhat more sophisticated ones, let's revisit one low-pass filter that we've talked about over and over in this course. It's the moving average filter. n+1 point moving average filter. Moving average is the most obvious thing that anyone would do to eliminate noise, right? You just take a window of values, of the past values, average them out, so that if there were some outliers due to noise, they get eliminated. Okay? So that's the idea. So y of n is what you're doing here is you're averaging x of n minus 1 to x of n minus m. The past m plus 1 values, because the current value is also involved. So to average it, you have to divide it by m plus 1. Does that make sense? Okay, so that's a filter, and you would think that as you increase m, this probably does a better job, looking more and more like a low-pass filter. So let's study that. Now we know everything. We know how to find the Z transform of this. We know how to find the frequency response of this. We can find the poles and zeros and use our geometric intuition to determine the frequency response. So first, what is the transfer function? Let's start with h of n if you like, or actually we don't need to go to h of n. Why would we? I mean, h of n is clear. I can do this on the side just for your information, but we don't need that. If a unit impulse were to hit, from the point it hits, its effect will linger for m units of time, and it will be averaged out to 1 over m plus 1, and then it will disappear. That's h. And in principle, you can take the Z transform of that. So if you just apply the Z transform formula to that, you're going to have 1 over m plus 1. 1 plus Z inverse. Remember, we take each one of this. This gets multiplied by 1. This gets multiplied by Z inverse. This gets multiplied by Z to the negative 2. And this gets multiplied by Z to the negative m. That's the definition of Z transforms, right? And each one has a value of 1 over m plus 1. That's why we have this coefficient. All right? Or instead of going through this circular path of first looking at the impulse response, you can do what we said to do earlier. You can just look at the difference equation. Where was it? Here. No, here. You can look at the difference equation and jump from that directly to the Z transform. So the coefficients are all 1 over m plus 1. So all of these b0 to bm are equal, and they are 1 over m plus 1. Okay, so that's the form of the transfer function. Now, where are the poles and where are the zeros? When you are looking for poles and zeros, it's useful to go from this Z inverse polynomial to a Z polynomial. Just divide and multiply by whatever you need to divide and multiply to make it look like a polynomial of Z and get rid of Z inverse terms, right? How would I do this in this case? Multiply by Z to the m, divide by Z to the m, so nothing's changed. But now you're going to be able to write the numerator as Z to the m to Z plus 1, and the denominator will simply be the Z to the m. Okay? So now you can tell me where the poles are. Where are the poles? They're all at 0. It's kind of interesting. Well, sorry. Okay? The reason is, in fact, for any finite impulse response filter, FIR filter, you're going to have an impulse response that looks like this one here, right? Just a finite number of terms in there. And when you take the Z transform, it's going to look like a sum of, H of Z will look very similar, except that you're not going to have all 1 coefficients. They'll change, right? But nevertheless, to bring it to this form, you'll multiply again with Z to the m and divide by Z to the m. And you'll have this denominator, Z to the m, there for any FIR filter. Okay, so that's a sort of a signature of an FIR filter, that the poles are all at the origin. So it's really the zeros that determines the behavior. Okay, so let's, and this is Paul. Why did I draw a 0, and why did you guys not tell me? I protest. Okay, so there are many of them here, m of them. Okay, now let's find out where the zeros are. Zeros are the roots of the numerator, which is this guy. Okay, so we need to solve this equation. Mth order polynomial. How do I even solve that? Looks complicated, but it has very special structure. All coefficients are equal to 1. That should simplify it. Here's a trick. This looks ugly, you know, too many things added, right? I'm going to multiply this with z minus 1 and divide by z minus 1. Times z to the m z plus 1. All right? So tell me what happens to the numerator. Does everybody see that? Is it clear to everyone that when I do this multiplication, I get this? If you don't believe me, just multiply them. You'll get all the terms multiplied by z, and then negative 1 will multiply most of those other terms with a negative sign. They keep canceling. Only the two edges don't cancel, and that's z to the m plus 1 and negative 1. Right? So by z minus 1. So what have I accomplished? I made the numerator look simpler, but I added some root z equal to 1 that actually doesn't belong there. That came from multiplication with z minus 1, right? So the zeros, therefore, are the roots of z to the m plus 1 equals 1, which are the roots of this, except the trivial solution z equal to 1, because that's artificial. That came because I multiply with this guy. Does that make sense? So z equal to 1 is definitely a solution to this, no question. But that's a solution only because of this term here. So we're going to, when we find the roots of this, we're going to drop z equals 1 from that list of roots. Does that make sense? Yes? Okay, so now let's, what are the roots? So, roots of unity. So, you can say 1 is equal to e to the j 2 pi times k, where k is any integer, right? Therefore, you can then say z is equal to e to the j 2 pi by m plus 1 k for k 0, 1, 2. You can keep going. But when k reaches m plus 1, you're back at 0, really, because you came back to the same z value. So you should stop at m, right? So this way you have m plus 1 roots. Which of these roots do I drop because it was artificially added by me to simplify the expression? 0. Get rid of this. All right? So that means all these roots are on the unit circle, as you would expect. And they are spaced apart by 2 pi by m plus 1. So you'll have a 0 here, whose angle is 2 pi by m plus 1. You have another 0 that far apart. You have a bunch of them, right? Depending on how long your impulse response is, how large your m is, you're going to get a bunch of those, evenly spaced. All right? there is one apparently at z equal to 1, but you remove that, right? So this is gone, so there's no 0 at 0, okay? So then, can you tell me what kind of frequency response I would expect from this? As I start at omega 0 and keep going, I'm going to visit 0 very often, right? Every time I'm passing through one of these frequencies, I'm going to hit 0 because I'm crossing a 0, right? So you're going to hit, so you'll start at 1. That's because you can easily show the DC gain is 1. Just from this expression, h of 1 is 1. Can you see that? Because z is 1, you've added 1 m plus 1 times, so you get 1. So that's why the frequency response will start at 1. It will quickly go to 0 at that frequency, 2 pi over m plus 1. Okay? It will make an attempt to go up, but quickly it will go back to 0 again at twice the frequency. Okay? And it will keep going down until it reaches pi. All right? So it's a low pass filter clearly because it passed high frequencies. I'm sorry, low frequencies. And then higher frequencies are getting eliminated. It is not a monotone response. It's not that, as omega increases, the response is gradually decreasing. It tries to go back up and then comes back down again. All right? But, it's very interesting. So you look at you have the structure of the difference equation. You turn it into a transfer function. The zeros of that happen to be uniformly distributed on the circle, and they stop a bunch of frequencies, and that's why you get that frequency response. So I think all those connections are quite fascinating. We can link anything to anything, right? The difference equation to impulse response, to Z transform, and to frequency response, poles, zeros, everything goes together. All right, so one last small discussion before I let you go. All pass filters, what are they? You've seen an example. I don't know if it was a homework problem. I don't know if I called it an all pass filter then. I think I did. So this is a class of filters that does nothing to the signal if you look at the magnitude. So when you look at omega, I'm now on the left part of this board. I'm going to talk about the continuous time case. So h of j omega is flat equal to 0, 1. What is not flat equal to 1 is the phase. Okay, and that's why these filters may be used. Sometimes you want to do a correction to the phase, but you don't want to mess with the magnitude. That's when you go to all pass filters. So if you remember our intuition about how poles and zeros of a continuous time transfer function h of s, so this is the S plane, determine the frequency response. Can you give me an example of an all-pass filter? Choose one pole and one zero so that as I walk here, I'm always equidistant to a pole and a zero. Remember, we are restricted about the choice of poles. The poles can only be, for stability, left halfway, right? So let me then just place a pole here. Let's call that point negative A, right? Where would you put a 0? Not on top of that, because that means 1. You didn't do anything. It's not really changing anything. The phase of that is also equal to 0. But where would you put a 0 so that the magnitude remains 1? Meaning that anywhere on this line, imaginary axis, I'm equidistant to both. A. Is it a problem that the 0 is on the right half plane? No, that doesn't change anything about stability. So now the distance to both is the same. Therefore, the ratio of the distances remains equal to 1. If you look at phase, of course, that's going to get messed up. It's going to be changing. But the magnitude will remain 1. So this was the continuous time case. Now let's look at discrete time. That is a little more cumbersome, less geometrically intuitive than this one, right? So I'll tell you the form, and then we can decide why that actually gives us magnitude equal to 1. So the general form of an all-pass discrete time system is this. 1 minus A Z inverse. A must be smaller than 1 for stability, because A is where the pole is. All right, so we have a pole at A, and then we have a 0 where? For which Z does the numerator become 0? 1 over A. Okay? So because A had to be smaller than 1 for stability, 1 over A, the 0, is actually outside the unit circle. Just like the continuous time case where the pole was in the left half plane, the 0 had to be in the right half plane. All right, so it turns out that this structure, the ratio of these two things, the magnitude of H is going to give us 1. So, all right, so it is convenient to show this, to factor out an A from this, a negative A, and then what remains is Z minus 1 over A. That shows us that the 0 is actually at 1 over A, and Z minus A. See, the pole 0 structure is much more clear in this form. All right, and then if I look at H of e to the j omega, it is equal to A times e to the j omega minus 1. No, not 1. 1 over A. And then e to the j omega minus A. So we're looking at the ratio of these two things, okay? And that ratio doesn't look like 1, but turns out it's a constant, and that constant is 1 over A, okay? So claim this is 1 over A for all omega, right? The reason is you can write them out explicitly. So for this guy, you have cosine omega minus A plus J sine omega. All right, so then to find the norm, you'll get, or if I square the norm, you'll get cosine omega minus A squared plus sine square omega, right? When you do the same thing for this guy, you'll get an expression, but when you look at those two expressions, you'll see that one is really A squared times the other, okay? And that cancels with this A, and you get the ratio equal to 1 for all frequencies. This is done explicitly in the notes, so you can look at the notes. So the most general form of a discrete time all-pass system is really a product of things of this form. So H of Z, Z inverse minus some choice AK, 1 minus AK Z inverse. If I have a bunch of these A's, and I multiply terms of this form from K1 to N, that remains an all-pass filter, because each of these terms in this product has magnitude 1, therefore their product has magnitude 1 also. Okay? So that's the most general form for discrete time all-pass filter. All right, let's stop here right on time, and happy Thanksgiving. And